Good morning, everybody. Welcome to this new lecture of the series Big Data for Engineers. There are news. Today, we actually continue to try to improve your experience and innovate. And what is new is that now we have a hand microphone that when she secured from multimedia services, we also secured the authorization of ETH to do so. So now we will circulate the microphone in the room so you can ask your questions directly there. You just need to be aware that this is publicly recorded and will be on YouTube. So if you ask a question in the microphone or on Zoom, if we unmute you, then please be aware of that. It is still fine if you do not wish to be recorded. You can just write on the Zoom chat or you can raise your hand in the room and just speak without microphone, and when she will repeat. All right, so I hope that this will make your experience even better. We'll have in the break also a quick presentation by ETH juniors who are going to tell you a bit. It's the junior enterprise of ETH, and they will tell you also a bit about what they are doing. All right, let's start. So first we need to finish that part about object storage, mainly how to store data in cloud services. And then we'll go into the Hadoop distributed file system. But before we do, I have two questions to ask you in order to see how much you followed of what I told you last week. We have a question in the chat first.
So the student said, I have a question from previous time.
Do you want to ask it over the microphone if we unmute you?
I think this probably from Zoom. So
yeah, it is from Zoom, but I think you can unmute people. We can try that. Let's see if that works. Do you want to ask your question directly in Zoom, or do you prefer that we repeat it? Yes, all right. So yes. You can try to find out how to unmute. I think it's possible in the chat.
Yes.
I think if you raise your hand, if you click here and raise your hand, it makes you be on the top, and then when she can directly find. Yeah.
I have already asked to unmute. I guess you have to.
Yeah. So we'll see if that works, and then the next times we'll know exactly how it works. All right. All right, let's just try to go ahead, and if you can directly read the question when she we'll continue to try, but yeah.
The question is that our block corresponding to one file stored in continuous blocks in a hard disk?
So blocks are actually something that we will discuss in details today, thanks to the Hadoop distributed file system. What I can already tell you is that yes, in a local drive, files are stored in blocks, and the blocks are not necessarily continuous. They are often that way. If you, for example, if you write a new file, then they will be written continuously if there is enough space. If the file grows too large and then you meet an existing block, then of course you cannot continue to write. So then you need to go somewhere else on the disk. Then it's not going to be continuous, but it's okay because the blocks are just reassembled by the computer itself. Actually, if the blocks are continuous on the disk, it makes reading through the file faster, because then you just continue with the head to just rotate the disk and go through. When you need to jump to a different place to read the next block, then that introduces a latency. In the 90s and 2000s, there was actually a tool in operating systems like Windows that was called, I think, the defragmenter. It was called the defragmenter, and you could run it periodically, like every couple of months. It would run for a few hours. And what it would do is move around the blocks on your disk to rearrange them in such a way that the files are contiguous again, that the blocks in a file are contiguous. So you see, your question is not trivial at all. The short answer is no, but we try to make them contiguous whenever we can. In more modern operating systems, the performance aspects have changed a bit, so it's no longer necessary to actually do that, or if necessary, it's done automatically. All right, I hope it answered your question. Otherwise, the second one, yeah.
So the question is general question about SQL. How can one nicely structure large and nested SQL queries? For example, in Python, we have functions and classes to structure code nicely.
That is also a good question. So it turns out in the SQL language that, of course, you have the query you can write in a single block, and of course they can grow a lot. You also have the possibility in many SQL products to define functions. So you can write functions that are going to return tables. There are several kinds of functions that can be available in SQL. Some of them are functions on single values that you can call in the middle of a query that do like plus. So you take two parameters, add them, return a value, right? And then you have the functions that return tables, that take tables and return tables. The support for this varies from product to product. Not all products support doing that. Functions that return tables are actually not supported by all products. I don't know from the top of my mind if PostgreSQL allows you to do something like that. But there is a way in many products to structure your query by separating it in functions. And we will see in the language that we will see later to denormalize data and gain in flexibility, JSONic, that we will have modules. So you will be able to even define different modules and functions that return enormous amounts of data that allows you to structure your code exactly like Python. Right? Did I answer your question? Yeah, all right. So now it's my turn to ask you questions. So let me switch to this one. It's about S3, and I'm asking you which one of these cannot be stored as an object in S3. Is it the first episode of Star Trek Discovery? Is it the 300 petabyte data set containing the proton collisions released by CERN? Is it the static pages of a website or an archived backup of your 2 terabyte hard drive? What do you think? All right, so you can vote either on your smartphone by downloading the ETH Edu app, or you can go in the browser by typing the same domain that you see on my screen, eduapp-app1.eth.th, and you can log in with your ETH credentials. All right, let's see your answers. Most people say it's the 300 petabyte data set. And actually, the majority is correct indeed. And why is that? Why can you store the other ones and not that one? I see in the Zoom chat an answer.
Yes. Some students say it's too big.
Yeah. What's the limit?
The max amount of a bucket is 5 terabytes.
Yeah, almost not a bucket, a file, an object, right? So an object has a maximum of 5 terabytes. A bucket can have plenty of objects, right? The bucket is a group of objects, right? And buckets can actually grow much larger than that, right? But yes, absolutely, you are correct. It is 5 terabytes. All right, and then it doesn't matter what you store as long as it's a file. Here's another question. What's the best practice recommended when you have an issue and it's too slow, whatever you are building? Should you first try to scale out, then try to make the code better, and then if it still doesn't work, try to scale up? Or first make the code better, then scale out, then scale up? Or first scale up, then scale out, then make the code better? Or you don't care? The order doesn't play any role, and one should just try everything. Answers are coming in. We have a majority. You like the second answer. And indeed, the second answer is actually correct. This is what I told you. The first thing that you should try is to improve your code. Store your data in a better way, in a more compact way. We'll see later how you can do that. Try to improve your code. Maybe there are inefficient parts in your code somewhere that you can make better. And once you have done that, maybe it will even fit on one machine and you don't even need a cluster. If it still doesn't suffice, then you can scale out by adding plenty of machines. This is what we saw that there are in the data center. You can just use even 10 machines, 100 machines, 1,000 machines. And then you can try to scale up, also have machines with more cores, with more memory. That's also a possibility, right? Okay, so let's now switch back to the slides and continue from where we were, which is the CAP theorem that I would like to say a few words about. So the CAP theorem. The CAP theorem is an impossibility triangle. You know, it's there's plenty of them actually that you find on social networks that you cannot have three things at the same time. Just don't exist. So you have to pick two, and the third one you need to give up. So what are these three things that we can have that we cannot have together, and we need to give up one of them in the big data world? This is as opposed to ACID properties that exist in typical relational databases with atomicity, consistency, isolation, and durability. This is the good old databases from the 70s, right? But it's very hard to achieve if you have a big data cluster to have this full ACID compliant system. Instead, this is how we view things. The three things that you cannot have at the same time are consistency, availability, and partition tolerance, CAP, and this is why it's called the CAP theorem. I have absolutely no idea why this is called theorem because there is no proof for that. Actually, it's not even fully formalized, so it's more of an intuition that people have, but it just got called for some reason a theorem. So let's call it the CAP theorem. All right, so I need to define these terms here: consistency, availability, partition tolerance, and then you will immediately understand how this actually works. The pivoting key of the whole thing is the partition tolerance. Because when you have a cluster of machines, or you have your data distributed all over the world in multiple data centers, the network can be partitioned. What does that mean? Maybe there was an earthquake, or there was a cable that was cut, and so on and so on, right? So basically, you might have parts of the system that no longer communicate together because they are disconnected. And the question is, can your system continue to function or not? Is the big question. And if it can, under which condition? So what you would like your system to have, ideally, first, is what is called the consistency. It's more exactly atomic consistency. What is atomic consistency? It's the idea that when you want to query the data and ask for some data, for example, that could be an object in S3, right? You would like to get back one of the objects that you've stored before. So if it's a cluster of machines, you need to pick one node to ask, right? Because if there's 1,000 or maybe there's 1 million nodes in S3, right? So there's 1 million different nodes that you could ask for that object. Atomic consistency means that whomever you ask in the network, whatever node you go to and ask for your object, they will all give you the same object. How can it be that they don't give you the same object? Why wouldn't they give you the same object? Any idea? In what case do you see they could potentially not give you the same objects? All right, I'm going to tell you then.
There is a
go ahead. Yeah.
Update delay, or data is replicated.
Yes, that's exactly these two things. The idea is indeed that the data is replicated and you might update your data. And if you update your data and put a new object that replaces the former one, it needs to be replicated. I have an animation for that, like this. I will come back to the other definition. So what happens? These are the computers. These are the nodes that are in your data center. Of course, I abstracted them away as points here. and they are connected via these lines. These are the network cables. What happens is that there is maybe an update somewhere. So this is a user that says, okay, please update my object with that new object. And this is then first done here, and then it should propagate to the other machines, right, to replicate the object. So it goes along the network cable, and the object is replicated. And then, bam, like in a Hollywood movie, something happens, and this is broken, right? Maybe this is the Atlantic Ocean, or I don't know, and there is an earthquake there, and then you can no longer communicate between Europe and America. So what happens, as you might have seen, is that the update here didn't manage to propagate all the way there. Right? This is still the older version. So now if you come and ask for a value, for example, to this node here, they will give you the new object. But if somebody else in Europe asks for the value, they will get the old one. So this is not consistent. They do not all return the same value, you see? However, the system is what we call partition tolerant. Why? Because in spite of this absolute catastrophe happening there, the system continues to work. People in America can continue to interact with it, and people in Europe can continue to interact with it. It's just that they might not see the latest values because it can no longer propagate between the two. So this is partition tolerance. And in that case, we gave up atomic consistency. It's no longer there. So the one thing that we kept, however, is availability for the A. It's the fact that there was the partition, the system is not broken, and it's well available in the sense that people can continue to go there and ask to update objects, to get objects, and so on and so on. That's called availability. Do you remember this 99.9999999 and so on, right? It's the idea that the system is there and in its work, right? So that's the A of CAP, right? So consistency, availability, and the partition tolerance is the idea that the system is designed to continue to work even in case of an earthquake. Right? And the idea is of the CAP theorem is you cannot have all three. And in fact, this is kind of the intuition in there. In that case, we have partition tolerance and availability, but we do not have consistency. We do not have consistency because you get different answers. There are also systems. So this is called then AP, right? This is an AP system. There are also systems that are that are consistent and partition tolerant, but not available. For these systems, they will continue to survive if there is a partition tolerance. However, maybe during a few minutes or a few hours, there will be a sorry, we're out of service message for a while, or you cannot instantly access it. And then it's restored and goes back to normal after a while. That's a system that would be consistent because it would never give you different answers, but it just stops everything momentarily and refuses to give any answers for a while until this is restored, right? So this is a CP system. And finally, there are the systems that are CA. These are the ones that stop working. If there's an earthquake, then that's the end, right? You basically, you don't survive that, and then you're not partition tolerant. So CAP, you have to drop one, C or A or P, and each one of the system will see during the lecture will drop one of the three. And you can ask yourself, okay, is it the C, is it the A, or is it the P that the system is dropping? So this is what the CAP theorem is about. Now, a bit of a warning, because there are marketing people out there that advertise their products. And the new cool thing that is done and that cloud provider loves to say is to say, okay, we managed to solve the CAP theorem. We are C, A, and P all at the same time, and that's it. You know, we are the best and we manage. Don't fall for it. It's actually not exactly true that they actually managed to do CAP. What happens is that they consider nowadays that the probability of a partition tolerance because of all the cables connected and so on is so low that in practice, since you don't care about partition tolerance, it looks as if the system were always consistent and available. However, if a partition happens, then this stops being true, and then either it will stop working or it will be not be consistent, right? And then, of course, the marketing people can try to hide that and say, no, you don't need to worry. It's always consistent and available. Yeah, if no partition happens. All right. So that's just a warning, because you will find at some places on the Amazon website, in some Azure papers, you will find these claims. Be careful about these claims, right? So far, the CAP theorem is still well accepted in the database community as being valid. All right, so this was the CAP theorem. Any questions on the CAP theorem? All right, there are no questions on the CAP theorem, so let's continue. And I encourage you in all the future lectures, ask yourself, with the CAP theorem, each technology we look at, is it C, is it A, is it P? All right. Here's the next thing that I want to show you. It's called the REST API. Right. It was very hype a few years ago, REST. It has to do with how you access the technologies we are going to look into. S3, Azure Blob Storage. There's many others. There's also AGFS we'll look into today. There are also Spark, MapReduce, and so on, PostgreSQL, and so on. All of these technologies need to be used by users. Somebody needs to access them. And the question is, how do you access them? Well, there are plenty of ways you can access these technologies. One of them is probably the oldest. It's a good old terminal, right? You in any operating system, you can open a window like that. Probably some of you did doing this git pull and at least git clone and git pull in order to get the data. But basically, this is a terminal, looks like a lot of text. You find a lot of them in older movies where the engineers are working on that kind of screens. And this is basically you type commands and then you get answers. Right? That's a terminal. That's the first way. Nowadays, we prefer to use fancy notebooks. It means that this is all hidden, and instead you have a very nice Jupyter notebook page that looks beautiful, and you type your queries, and it's interactive, and so on and so on, right? So there's the fancy notebook interface. You can write Python, you can write SQL, you can write all type of things. So this is another way of interacting with a system. There is yet another way that's called using a host programming language. What does that mean? This is for advanced users, power users. These users are also going to connect to S3 or MapReduce or whatever, but they are going to do that with a computer program. They are not going to themselves put the things in a notebook. Instead, they are going to use a Java or Python or C++ program that automatically connects to the system and does whatever they want to do automatically. They will create objects, remove objects, execute queries. It's all in a program automated. This is called the host programming language, as opposed to, for example, SQL, that is the actual language of the system. And the host programming language is outside of that. So Java might create SQL queries that it sends to PostgreSQL and then get back the tables, right? But Java is then the host programming language, and SQL is the actual programming language of the platform you're connected to, right? And finally, there is a fourth way that is called the REST API. In fact, that fourth way is very often used by all of the others. Very often, all of them, without telling you, they actually use a REST API. They just hide it. So now I have to tell you what is a REST API, right? All right. So REST first means not hypertext transfer protocol, that's HTTP. It means representational state transfer. You don't have to care why it's called that way. It means representational state transfer, but you don't have to worry about that. Just REST. Everybody understands when you say REST. So what is REST? It's actually using the HTTP protocol. So you know that the HTTP protocol is the web. That's the protocol used when you access a website and visit the ETH website or whatever. It goes over the World Wide Web, invented by Sir Tim Berners-Lee 30 years ago. Doesn't make us any younger. And the way that it works is that you have this sort of fancy strings that you type in your address bar. You probably saw them already. I mean, who didn't see that by now? This is called a URI or a URL, or there's many names for that, right? So we tend to call them URI when we talk about REST. It means Universal Resource Identifier. URL is Universal Resource Locator. Usually we use URL when you type it in your browser. But in a REST API, we say URI. All right. What is it? It's a resource. For example, a resource can be a web page, an image, an object, a bucket, so anything. In REST, every resource is identified with something like that. So now I use example.com, of course, but that would be the domain that you're actually using, right? eth.ch, amazon.com, and so on. So the idea is that it's made like this. First, the scheme. It's usually HTTP, right? Very often, maybe HTTPS if you want security. Then you have the authority, that's the domain. Anybody can buy them, and most companies have one, right? Then you have some path, right? That has /////. So it's a series of directories, basically, right? Then you have sometimes question marks. If you observe in your browser, you might sometimes see them. This is typically when you fill forms. And then you see what is called a query. So this tells you that the variable ID is associated with the value foobar, with the equal sign, and so on. That's called a query. So this is also part of a resource. And finally, we have sharps. This is called the fragment. It's, for example, if you're on Wikipedia and you want to directly jump to a specific section of the Wikipedia page, you will notice that it's a sharp that does that. If you have the sharp with the name of the chapter and you type that in the browser, it will immediately jump to the place of the page corresponding to that. That's a fragment, right? So you just need to know, if I give you a URI, you just need to know what it's made of and recognize all of these components, right? Okay, so now that we have that, what does it mean? Well, now the objects and the buckets, for example, with S3, can now be identified with such URIs, right? This is how the REST API works. For example, you might have bucket with whatever name the bucket has, .s3.amazonaws.com, that's the domain of Amazon. And an object, it's the same thing / the name of the object. So in orange here, you need to replace with the name of the bucket, the ID of the bucket, and the ID of the object. So these are your resources. Don't try that to put that in your browser, it will not work, or at least maybe not as you might expect, right? Because this is not meant to be entered by a human in a browser. It's meant to be used by a computer program. So we have these resources that you can see them as identifiers. It's like the AHAFA or AVS number in Switzerland that identifies people. This identifies objects and buckets. All right. And what we do with them is, in addition to the resource, we have also what's called a method. A method is a verb. And there's 4 of them you need to know. There's others, but these are the 4 I want you to know. Get, put, delete, post. You will see that it's extremely intuitive to understand what they do, because what they do is that they get, they put, they delete, and they post. So get gets you the object. So if you say get with the URI of the object over HTTP, right? Then you get back the object over HTTP as well, right? So you send get the URI of the object, and over the network, you receive the bits of the object that you have asked for, the picture or the video or whatever. This is get. Get is side effect free. It doesn't modify anything, right? It just gets whatever value the object has, it just gets it and gives it to you, right? Second, put. Put is for for updating an object. If you already created an object before you want to update it, then you just say put and then the UI of the object, and then also, of course, the new content, the sequence of bits of the new object, and then you ship it over to AWS, and then it will automatically update the object and confirm, acknowledge that this is done. Right? So this is put. Put is idempotent. If you do it twice, it doesn't bring you anything more than if you do it once, right? If you just say twice, put that new object in there with the same content, that's useless. So this is what idempotent means. It can the same, idempotent. I think that's Latin. All right, then we have delete. Delete with an object URI will just delete the object. That's it. And then after that, if you do a get, it's gone. It will be, you might know the 404 error, not found, HTTP not found 404. That's an error code of REST APIs. And if you do a put and you do a get after that, then you will get back whatever you put in there, right? You put it there and then you get it back. Right? It's really intuitive, right? Get, put, delete. And post is actually when you create, you don't know the ID yet. You just want to create a new object. You say, okay, create a new object, right? So this is typically done with post. It's actually a bit of the one method for everything else. So basically, if you know it's get or put or delete, you use them. If you don't know, it's going to be a post, right? So this is kind of the last resort when you don't know how to do it, and people use the post verb. All right, and that's the most generic one. It can have side effects, so you need to be careful about that one. All right, and once we have that, the resources and the verbs, what happens is that the way people interact with the REST API with the cluster is put a bucket, delete a bucket, get a bucket, put an object, delete an object, get an object, and so on and so on. And when you have an API like that, it's going to nicely work. And then you can implement a terminal window or a Jupyter notebook or a Java host programming language on top of REST, right? So this is why almost every single technology that there is on the market, in databases or big data and so on, almost all of them have a REST API, almost all of them. And I'll show you around for HDFS and others, the kind of REST APIs they have. It's almost guaranteed they have one, because this has become kind of a standard now. That database products have that. But you as the final user, you don't really you're not going to really use that because, again, this is hidden inside the system, and what you will use typically is the Jupyter notebook, or maybe a terminal window, or maybe a host programming language if you want to do something fancier, right, with Python, for example. But it's good to know that this exists. This is actually the way the web works, HTTP, and this is how many database products actually work. Do we have a question?
So, out of curiosity, what alternatives are there to REST?
Several. So the first alternative that there is what is called a proprietary API. It means that the company who designed their product just does whatever they want. So excuse me. For example, I think MongoDB, for example, is a database. It's a proprietary API. I don't think it has a REST API. Maybe it has now, but back then it didn't. And then what you need to do is install a pilot. You need to download what is called the pilot and install it, and then you are able to communicate with the product. The advantage of REST is that you don't need to download any pilots. It's just over HTTP, and every computer understands HTTP. So that's the first way, that the product invents their own interface, and it's proprietary, and only them know how it works. Another way is called SOAP, like the actual SOAP, S-O-A-P. I don't remember what it means, but it was an ancestor of REST. Before REST existed, people used SOAP. And SOAP was also using HTTP, but it was much more complex, using XML syntax and so on, and almost only post requests all over the place, which was actually a cyber security issue. So SOAP is also an alternative to REST, but nowadays REST has really become the one main standard that many implement. Right? Did I answer your question?
There is an answer in the chat actually. He said GraphQL.
GraphQL is a complement of REST. You can use REST with GraphQL. So you can have a REST API and you ship GraphQL code and get back some JSON data. So GraphQL in that sense is not a competitor of REST. It's a friend of REST. You can use GraphQL together with REST. And I think it was even what it was made for. When GraphQL was designed, its goal was to be used with REST APIs in order to fine-tune the sort of the GET request that you have on the data. The GET would get everything, and if you add a GraphQL, then you can take a smaller subset of the actual data you want. Right? Did I answer your question? Right. Do we have another one? Another question?
He said yes.
Oh, it's I see ETH juniors. So nice that you're here. I will give you access during the break. All right. Okay, now here's next. I told you it's a flat, S3 is a flat list of keys, right? It's just a key value model. You have object IDs and object values. So actually it works like that. However, the slashes are usually something people interpret as directories, even though these are not actually directories, but usually people understand them as directories. So actually when you look at these object IDs, this is what people understand. What you need to understand is that this is a simulation. It's not actually stored like that, but if you go to the user interface of S3, you will actually see a nicely fancy presentation like this. You just need to know that physically it's really strings with slashes. That's all it is. Second, S3 and also Azure Blob Storage that we will look at is very, very popular with static website hosting. It's when you want to have a website, but there is no PHP or anything dynamic. It's just a page that is always the same. The pictures are always the same. The sounds and videos are always the same. Then it's very, very cheap and popular to just drop all your images and web pages on top of S3, and then you get a URL for free that people can put in their browsers. You can even redirect it to some domain and hide it. So S3 is a really, really great way of storing static websites for a very cheap price, right? JSONic, for example, the language we use, jsonic.org, is actually on S3. It's all the pages are on S3, and if you type jsonic.org, you can try, you will actually see something that comes from S3 over the web. And since it's a web page, then of course it can be displayed in the browser. All right. And another thing you can do with S3 besides web pages is dataset hosting. That's the whole reason we are doing all that, right? So we can actually store data. And so here you see it sounds like weird. There is AAA, AAB, and so on. This is just because these are just obscure names of the parts of some data sets. because I partitioned it. We'll see that we love to partition data sets. And these are just the parts of some huge data set. I don't know, maybe that's weather data, or I don't know what that is, right? But it's just stored as plenty of S3 objects, and later we'll see how to query them. But the first use case for S3, for the purpose of our lecture, is that you can just drop your data in there, just like that. That's what a data lake is about. You can drop your data sets in there. You can store them even as multiple files and multiple objects if necessary. And that's it. Then you can go ahead and start querying it. All right. Other features of S3 is that you can also try to have a cheaper price, but then it's for backups, basically, that you agree that it takes hours to get anything. That's called Glacier. That's very cheap, but of course, you would not use that for a website, right? People are not going to wait for hours to see the page, right? So there are options, basically, to fine tune how that works. All right. So this is Amazon S3, which was kind of the pioneer in there. There is another one called Azure Blob Storage. That is the one by Microsoft Azure. I will very quickly tell you about it, but since you know S3, it will be easy to learn blob storage because it's very similar, right? So I'm just going to tell you a few differences. So the main difference between they do the same thing. They are both a cloud storage service. In S3, we have buckets and objects, right, to identify. We have a bucket ID and an object ID. In Azure, instead, we have three things. You have first your accounts. I don't know if that's your email address or some name that you invented for your account, right? So you have your accounts. Then you have the container, that would be the equivalent of the bucket in S3. And then you have the blob, that is the equivalent of the object. Actually, O means object here. It means binary large object, blob. Right? It's just a fancy word that people love to use, blob, right? Blob. All right. So what you see, the only thing extra is the account. In S3, you don't have an account, but the bucket names must be unique worldwide. If somebody took it, then you can no longer take it, right? But in Azure, since you have your accounts, then people can use the same container names if they want. Second difference, in S3, the object is a black box. In Azure, you have an explicit exposure of blocks. You have block blobs, append blobs, and page blobs. So there are several kinds of them. Block blobs are the ones who are into SCD. This is for data sets. Append blobs is for logging, if you keep logging stuff. And page blobs are for virtual machines, when you want to have some persistent memory in virtual machines. So these are a bit less relevant, but block blobs are important. So here you see that there are blocks. In S3, we do not actually expose the blocks, right? So I'll tell you more about blocks with HDFS, the lecture that is coming. So this is why I'm not telling you about Azure. So you could kind of say that Azure is kind of hybrid between S3 and HDFS that we are going to see, right? Because it exposes the blocks, right? And because it has blocks, it can grow bigger. We will see in HDFS how that works. So the limit here is 5 terabytes. But in Azure, you can actually go all the way to 190 terabytes, much more than a hard drive. Why? Because we have the blocks, right? But again, I stop about blocks here because we're going to talk about blocks during an hour more today. So this is why I don't tell you much more than that. And here you have the limits for the other two, but again, they are a bit less important, right? For us, for querying data. Append blobs go to 200 gigabytes and page blobs to 8 terabytes for virtual machine memory. All right. So the way it works in Azure, so here, that's something they tell us. In S3, they won't tell you. I have absolutely no idea how it's implemented. They don't tell much about it. But the good thing is that Azure tells us. So in Azure, it might be the same in S3, I don't know, but in Azure, they have these racks with the towers of computers that I told you about last week. They typically have between 10 and 20 of them, right, 10 or 20 racks. And each rack has 18 levels there, 18 computers and hard drives and so on attached to them, right? So they have this huge part of the data center. It's probably an entire room in a data center. They call it a storage step. Now it's very easy to compute how much data you can store in there. It's actually 30 petabytes. It's just a multiplication. Just compute what you can have on one of the nodes and times 18 times 20. That gives you roughly 30 petabytes. The other thing they do, because they have plenty of them worldwide, they have probably one in Zurich, one in Frankfurt, one in New York, I don't know, all over the world, they have these storage stems. And they try to keep them below 80% of capacity. As soon as there is more than 80% of that is used, they try to move it somewhere else, right? They try to stay below that capacity. I'm pretty sure you've all experienced what happens when your hard drive is full, and that's not a pleasant experience. So that's the reason, right? They just try to keep it below 80%. All right. So the way it works, also the details that probably happen in S3 as well, but they won't tell us, but in Azure they do. The idea is that within a storage stamp like that, they do replicate the data, right? So the same blob or object is going to be replicated when you store it. So you're going to wait until it's replicated 2 or 3 times, I don't know, and then it confirms that your object was successfully stored. Then once you're done, but this is then asynchronous. So this is synchronous because you have to wait. Asynchronous means when you're gone and do something else, it's going to start replicating it across the world. So maybe you start it in Frankfurt and now it's going to make a copy in New York, a copy in Beijing, and so on and so on. This is how it works. So this is called replication. And I'm also going to talk about replication in HDFS. So again, I'm going to come back to that, the notion of replicating data. Why do we want to replicate across regions like that? Right. So there's 2 main reasons. First, latency. If your customers are all around the world, then it's best if you can serve them from wherever they are. If all your computers are in the US, it's going to take too much time, a latency, if people connect to it, for example, from China. So this is why you have to replicate your systems also in China in such a way that they are closer, right? Because there's a speed of light. Communication is not instantaneous, right? So this is one reason to have it all over the world. The other reason is the resilience to natural catastrophes, because that way, if there is a natural catastrophe somewhere, then your data is also replicated somewhere else and you're safe, right? You know that your data is going to have copies at another place. So this is also a reason, an important reason. And that actually happened. I remember a few years ago, there was, for example, a fire in a data center in Eastern France, where actually it was absolutely tragic because they actually lost data because the data was not replicated to other places, and some customers actually lost data. So just to show the importance of replicating your data at different places so that you do not lose it if anything happens. Do we have a question? Before the break, so in the chat.
Sorry, I just muted myself. So a data center will be made up of several storage stamps, which contains several racks.
Yes, you could say it like that. I can imagine you can also have multiple storage stamps in a data center, multiple racks in a stamp, multiple nodes in a rack, multiple hard drives in a node. And then you can have also multiple data centers, right? So indeed, data center, storage stamp, rack, nodes, and then the individual drive. However, storage stamp is specific to Azure Blob Storage, right? So be careful with that. This is really a blob storage thing. The notion of data center and rack and node and hard drive, this is for everything. That's always there, right? So you just need to be aware that storage stamp is a blob storage world.
Another question is that, yeah. What is the typical latency for data to go from US to China, for example?
So I think that I see another answer below. That's typically this, right? So typically the latency can be, if you're really close, you can have a few milliseconds. Like video game provider, for example, love to be close to your home to have a good latency. As soon as you go on the other side of the planet, you can be above 100 milliseconds or a few hundreds of milliseconds quite easily, in fact. Because the light doesn't propagate, well, light does, but the actual data doesn't propagate in a straight line. It just goes back and forth at a lot of places, so it's actually slower than the speed of light. So you can really expect a few hundreds of milliseconds, and I can really tell you, you feel it. If you connect to a website or a service and you have to, this sort of latency, you feel it. So this is why you need to really also have servers close to where people are. And most big companies do have servers all over the world for these reasons. And we have a third question before the break.
Yes. So what about the regulation, for example, the Europe Data Protection Law?
So indeed, what do the regulations say actually? They basically tell you where your data should be stored and what you need to store. So of course, everybody has to follow that. What it means concretely is just that you would not be authorized to go everywhere. For example, in the EU, you have to put your data there, then you can maybe put some in Sweden, some in Spain, and so on, just to replicate, but only within the EU, right? So that's what protection laws basically do. So just because you can store it everywhere does not mean that you are allowed to store it everywhere. Right? So of course, every company must also obey the law and comply with wherever it needs to. So, for example, Swiss banks probably cannot store it anywhere else than in Switzerland because of the banking secrecy laws. All right. Doesn't mean they cannot replicate it in Switzerland. You can put some under the Alps, some in the Jura Mountains, I don't know. So there's ways you can also replicate with Switzerland. All right, let's take a break. We have ETH Junior, so during the break, you'll have a presentation. I will make you a co-host. You can stay if you want. If you want to go outside, you can go outside. Feel free, it's optional. And I'll see you in 10 minutes for the HDFS lecture about that, right? So I'll see you in 10 minutes, and I'll now let Ms. Janelli have the word.